Hello. Today we're going to talk about the 4.3 curve sketching. In 4.1, we discussed applications of the first derivative. We know we can use first derivative of a function to determine increasing or decreasing of a function. When the first derivative is positive, the function is increasing. When the first derivative is negative, the function is decreasing. In 4.2, we discussed the applications of the second derivative. We know we can use the second derivative to determine the concavity of the function. When the second derivative function is positive, the function is concave up. When the second derivative is negative, the function is concave down. So we can combine all the information to try to sketch the graph, but we also need some other information and some other techniques, including the limit, and try to complete the whole graph. Typically, a guide to curve sketching includes the following 9 steps. Step 1, determine the domain of f. That's always the first thing to do. Step 2, find the x and y intercepts of f. We want to locate some spatial points on the x and y axis to help us to draw the graph. Step 3, determine the behavior of f for large absolute values of x. So those are called the end behaviors, and we want to know the basic shape of the curve, especially at the 4 ends. Step 4, find all horizontal and vertical asymptotes of the graph of f. We do not always get the horizontal or vertical asymptotes, but we should always check it. Step 5, determine the intervals where f is increasing and where f is decreasing. So that's the first derivative. Step 6, find the relative extrema of f. We can use either first derivative test or second derivative test. Step 7, determine the concavity of the graph of f. So that's the second derivative. Step 8, find the inflection points of f. That's the second derivative. Step 9, plot a few additional points to help further identify the shape of the graph of f in the sketch graph. So let's do a simple example and do it step by step to sketch the graph of y equal to x cubed minus 6x squared plus 9x plus 2. Step 1, the domain of the function is all real numbers, this polynomial function. Step 2, plug in 0 for x to get y-intercept equals 0 cubed minus 6 times 0 squared plus 9 times 0 plus 2, we get a 2. To find the x-intercepts, we just plug in 0 for y and solve the equation of x cubed minus 6x squared plus 9x plus 2 equal to 0. But this is a cubic equation and it's hard to solve, so we just skip it. Step 3, end behaviors. So we try to find the limit of the function as x approaches infinity, and we get positive infinity. Similarly, we can evaluate the limit of the function as x approaches negative infinity, and this time we got negative infinity. So that tells us the function goes up with a bound on the right and goes down without bound on the left. So from information in step 3, we know that the function does not have a horizontal asymptote, and it also has not doesn't have any vertical asymptote because it's polynomial function. The vertical asymptotes usually appear in the functions with some denominators. Step 5, increasing and decreasing of f. So we take the derivative of the function, we get a 3x squared minus 12x plus 9, and set equal to 0 and to solve it to get the correct numbers. So we get a 3 times x minus 1 times x minus 3 equal to 0 if we factor the left-hand side. So there are two critical numbers, x equal to 1, x equal to 3. And those two critical numbers divide the whole domain into 3 regions. In the region from negative infinity to 1, we can pick x as a test value to find f prime of 0 equal to 3 times 0 minus 1 times 0 minus 3. So we got a 9, which is positive, so f increases. In the region from 1 to 3, we can pick x equal to 2 as the test point, and find the f prime of 2 equals 3 times 2 minus 1 times 2 minus 3. We got negative 3, so f decreases. In the region from 3 to infinity, we can pick up 4 for x and plug in to the f prime to get the f prime of 4 equal to 3 times 4 minus 1 times 4 minus 3, so we got 9 again. So that's positive. F increases again. So from step 5, we know the function attains the relative maximum at x equal to 1. From negative infinity to 1, the function increases, and from 1 to 3, f decreases. So there is a maximum of the function at x equal to 1, and the function value at that point is f of 1 equals 1 cubed minus 6 times 1 squared plus 9 times 1 plus 2, which is 6. Similarly, at x equals 3, the function attains the relative minimum, because in the region from 1 to 3, the function decreases. And from 3 to infinity, the function increases. So there's a minimum at x equal to 3. And the function value at x equal to 3 is just 3 cubed minus 6 times 3 squared plus 9 times 3 plus 2, which is 2. Step 7, concavity of f. So we take the second derivative to get the 6x minus 12, and set equal to 0, we get x equal to 2. And that would divide the whole domain of the function into 2 regions. The first region is from negative infinity to 2, and we can pick x equal to 1 as the test point. And evaluate the second derivative of the function, and we got the f double prime of 1 equal to 6 times 1 minus 12, which is negative 6. So that's negative, so that means f concave down. In the second region from 2 to infinity, we can pick x equal to 3 and evaluate f double prime of 3 to get 6 times 3 minus 12 equals 6. So that's positive. So that means f concaves up. Step 8, from step 7, we know x equal to is the inflection point for the function, because it changed the concavity at x equal to 2. From negative infinity to 2, it's concave down. From 2 to infinity, it's concave up. And the function value at x equal to 2 is just 2 cubed minus 6 times 2 squared plus 9 times 2 plus 2 equal to 4. So finally, we can pick up another point x equal to 4 to get the f of 4 equals 4 cubed minus 6 times 4 squared plus 9 times 4 plus 2. We get 6 again. So we can plot all those points and use all the information about the increasing, decreasing of the curve and the concavity to draw the graph, and it shows in the lower right. So this is the end of this section.